Hi everybody, how are you? We're going to go through now the remainder of this section. All right, I'm starting here with the kinetic theory of gases. I'll lead you into ideal gas then, and we will finally deal with this equation of state for an ideal gas, and we'll elaborate on as we go along. I'm starting with the kinetic theory then. Will everybody make sure that they would be recording details of this as we go along now? You should all have an A4 pad and a pen in front of you, and I'd like you to scribble away on the content of this class. There are notes on this that will follow, okay? But it's very important you're taking your own notes as well on material I cover with you, right? Good. Now, the kinetic theory, we're starting with that, and I'd ask you to be careful in relation to how you present it now. A theory is simply an explanation of facts that we already know, and it would be very important that you wouldn't be reading any more into this. The theory is devised so that you will have a better understanding of gases and their behavior, right? So it's very simple, and it's based on certain assumptions that I'm going to deal with now. First, before I do that, I'm just saying to you there that this theory explains many of the properties of gases and the gas laws. And immediately under it, you're just told there about Brownian motion. Can I make a brief comment on Brownian motion for you, please? Brown developed a concept that gases were particles that were constantly moving. And it's very important that we understand that what we have is a sealed container and there's particles running around inside it. Now, they are, according to this particular theory, they're in constant random motion. Brown looked at smoke particles in a sealed chamber, and he found that these big lumps of soot, which is the smoke, was darting around the place in an erratic fashion inside the sealed chamber. And because of that, he came to the conclusion that the smoke particles were colliding with much smaller ones called the gas particles, and that they were causing the random motion. So every one of these particles is darting around there, colliding with everything around it, including the walls of the container. And so it's quite irregular, and you need to realize it's random, okay? Constant random motion. That's the model of a gas that we would develop with that. Now, the kinetic theory is what it says. It is a theory to explain what's happening. Now, I've developed this point already, but let me mention it again to you. A theory simply is our way of justifying what is actually happening. And it's very important for you to work with that in mind, that you have a sense of that, okay? That you are dealing with a theory. You're dealing with, something that happened and you're trying to justify it. Sometimes they're simplifications, okay? So we have to be careful with that. The kinetic theory of gases is based on the following assumptions. Now, let me just say a few words about assumptions, because I need you to understand there is no scientific basis for assumptions. Okay, there is no scientific basis. It's our way of simplifying matters so that you'll understand it better. So the assumptions of the kinetic theory are a list of observations that were made, and I hope you will find them useful. Now I'm going through them. Number one, the first assumption is that the particles of a gas are in constant random motion. Now that's a clear statement that they're moving all the time, and that their movement is quite erratic. And you have to work on that basis, and when you're actually doing that, you'll have no issue with it at all, but it's very important that you'll be aware. Constant random motion. Number two, the assumption number two is that there are no attractive forces between the molecules. Now, as a chemistry student, you should well be telling me, I don't know, is that correct? I'll deal with it later, but just take it for a moment that that is one of the assumptions, that there are no attractive forces between the particles. In other words, the particles are moving totally independently of each other. They're for all the world like little metal balls bouncing off each other permanently as they go around there, okay? So they have no attractive forces for each other. Number three states that the gas molecules occupy no space. Now, that's not correct, but I mean, we have to accept it's an assumption. I suppose what they're really saying is that the particles are extremely small. That's what they're really saying. The particles are extremely small, and consequently, they take up little or no space. And for simplicity, then, we say they occupy no space. And I think you'd want to just accept that as face value there. Number four, the collisions between the particles are perfectly elastic. Now, that's fairly technical, that one. You need to be careful with it. An elastic collision is a collision where there's no energy lost. If the truth is known, There is no such thing as an elastic collision. Every collision involves the loss of some energy, but these collisions are close enough to it. So for simplicity, we say they are perfectly elastic collisions. And I hope that that's okay just in terms of what we're doing. And the last one I've listed for you here is the kinetic energy of the molecules are directly proportional to the temperature. It is suggesting if the temperature went up, that the speed of the particles would go up. But that's saying a bit more than that now. That's saying that if you double the temperature, you double the speed of the particles. And that's technically not right. But we accept it as a simplification. And that's quite okay. So now you'd be expected to know those 5. There are more there, but 5 is adequate for leaving cert. And I've put them in a particular order because I need to go back on them now and qualify the flaws in them. We need to understand that. So if you wanted a simple model of a gas, then it would simply be nothing more than this, okay? It would be a sealed container, right? And all these particles running around inside, constantly moving, bouncing off each other on the walls of the container. That's what we know as a gas. And from that point of view, I think you have to kind of accept that's a good model. Right? There are no attractive forces between the particles, is stated as well. No attractive forces. The molecules are so small, they occupy no space. The collisions between the particles are perfectly elastic, and the kinetic energy of these particles or molecules is proportional to temperature. Now, I've put them in that order for reasons that I'm about to illustrate now. So let's take it then that that's the kinetic theory of gases. What is it? It's a theory which explains the behavior of gases. And it's based on certain assumptions. And the main assumptions are there for you now. Now, I've told you that the order is important as well because we'll use them to justify them. What is likely to happen in leaving cert is they will ask you to give 2 assumptions or 3 assumptions of the kinetic theory of gases. And I would strongly recommend the first 3 to you. That would be far better because you'll be able to deliver on them, you'll be able to defend them much better on the basis of the course that you're studying. Now, let's move on from it for a moment, please, and have a look at this. There are certain limitations. There are certain limitations to all assumptions, okay? Like an assumption would have no basis in fact, okay? We simplify things by assuming certain things, and that's most important, right? So in this instance, the limitations of the assumptions are there for real gases. Everyday gases like oxygen and nitrogen that you might prepare in the lab, well, they would go close to them, but there would be limitations, and we need to understand what those limitations are. And I'm about to develop them with you now because that's very important, okay? The assumptions above will hold for an ideal gas. Now, I'm coming to that next, the ideal gas, so bear with me. The ideal gas is the perfect gas. Okay, the real gases are everyday gases that we use in the lab, that we prepare, that's in the air, etc. Right? So they're real gases. But the ideal gases are a concept again in chemistry to help us understand the behavior of gases. Now, you would be asked, what are the limitations? First of all, they'd ask you for some assumptions of the kinetic theory, and then they'd ask you, what are the limitations of these assumptions? Now, let me suggest this to you. You should work from the top down in terms of getting the best marks in your exam in this. And I hope you'll take my advice on this now. I've put an asterisk on 2 and 3. And I've put them in that order, 1, 2, 3, 4, and 5, because I'd like you to use 5 only when you're desperate. And 4 likewise. Okay? Use 1, 2, and 3 all the time if they're asking you to list assumptions, list 1, 2, and 3. If they're asking you for limitations of those assumptions, you're best equipped to defend numbers 2 and 3. I'm going to do that with you now. I'll work down through them sequentially and tell you there's a flaw in every assumption. And here we go with that then. I'm asking you just to be aware of that. First of all, the particles are in constant random motion. If you could imagine 2 gas particles flying through the air, and they would collide with each other, and they'd bounce back again. Now, if you could imagine that happening, then you have some sense of what's going on, that somewhere there along the way, these particles became stationary before they moved off again. So isn't it correct to say that they're not in constant random motion, they're just in random motion most of the time? And that's the flaw in that there is a point where when particles collide, there is an instant where they become stationary before they move off again. So the word constant is flawed there. They're not in constant motion, they're only moving most of the time. So that is a limitation of the first one. The second one, of course, there are no attractive forces between the gas molecules. Now that is loaded with error, and as a chemistry student you should be all shouting at me and saying rubbish, because you know there are intermolecular bonds from another part of your course. Could you name those intermolecular bonds? You have van der Waals forces, you have dipole-dipole forces, and you have hydrogen bonding. Very good. They're the three intermolecular bonds. And the type of intermolecular bond is the bond that attracts molecules together. Now, you have another section of chemistry you must revise to go back on that. Make sure you know it, please. It's very important. All right, and we're working on that premise now that everything is okay. I hope it is. So I'm asking you just to be alert to that because there are issues with it, okay? But that's an excellent one because you have a lot of chemistry to defend number 2, okay? If the molecule is non-polar, then it's van der Waals. And if it's polar, it's either dipole-dipole or hydrogen bonding. So you'd well be able to say there are, that assumption has limitations, which is what you're supposed to do really, okay? The third one then, the gas molecules occupy no space. There's my model of a gas here, very simple, sealed container, okay, dots inside it, okay, and they're running around inside it, okay. And I'd be saying to you, the dots here, they do not cover any of the board. And of course that's not correct. They cover very little of the board, but they do occupy some space. There is no such thing as a particle that occupies no space, okay, no matter how small. And that would be very important. I often use the analogy of dust for this, that you come into a room and there's plenty of dust around, but you can't see it. Yet if you were to bring a vacuum cleaner in here and you were to suction up the dust, you'd fill a bag. So that material must be in the air somewhere, but we can't see it. The particles are so small, we can't see them. So that's very important that you realize that's the flaw in that. Every particle, no matter how small, will occupy some space. Very good. Number 4 there, collisions are perfectly elastic. I've already given you away on that. That's not an easy one now. There's a bit of physics in that. Avoid it. Choose the others first. Be wise about that. The likely question now I'm reminding you again is, you'll be asked, give 3 assumptions of the kinetic theory and suggest limitations to the assumptions you have named. So please, select the right ones so it will make life easy for yourself. There is no such thing as a perfectly elastic collision. I've mentioned that already to you, and I'm going to leave it at that. Whenever particles collide, some energy is lost, therefore it's not perfectly elastic, right? And the last one here, the kinetic energy of the gas molecules is proportional to the temperature. The flaw in that one is the proportional word. It's suggesting if you increased one, you'd increase the other. If you were to plot a graph according to that assumption, if you were to increase the temperature, you would increase the kinetic energy, something like that. That doesn't happen. What happens is, if you increase the temperature, yes, you'll increase the kinetic energy, but they're not proportional to each other. Proportional would mean if you doubled one, you double the other. That doesn't happen. If you increase the temperature, you'll get a slight increase in the kinetic energy of the gas particles. So that's the flaw in that one. Now, I've asked you already, I'm repeating for the last time now, please nominate them in that order and you'll find it easier to handle them. They won't be asking you for 5, they'll ask you for some of them, which you choose yourself. So for real gases, there's a flaw in all the assumptions of the kinetic theory. So let's move on then a little further. Under what circumstances could we get gases to behave better? First of all, now I must mention again ideal gases to you. The assumptions above will hold for ideal gases. Okay, an ideal gas is a gas which is the perfect gas. I'm going to define it for you in a moment. It's the second part of this unit now. Okay, but it's the perfect gas. Okay, the ideal man, the ideal woman doesn't exist. Okay, and so will we accept there isn't an ideal gas either? So that's what you're dealing with, the assumptions. Okay, that would be, the assumptions would hold if it was a perfect gas. But it's not. Everyday gases are not perfect, and that's what you're dealing with there. All right? Now, you would be asked the question, and I had it in the study plan already, under what circumstances would a real gas behave like an ideal gas? And the answer is there. Low pressure and high temperature. And I'm drawing 2 little containers again for you now. There's one container with a gas in it, and there's a second one. I'll give you some idea. Low pressure and high temperature. There's a gas at low pressure. There'll be very few collisions. there's a gas at high pressure. Now, so with a piston then, if you pushed in the piston in the gas syringe, you would of course give the particles less space, and consequently there'd be more collisions, so you'd have a higher pressure. So that's much lower pressure than that. That's low pressure, and that's high pressure. And that's the whole idea, right? You've just got more particles, or less space if you like. If I were to cram that together, the pressure would get bigger as well, okay? So low pressure would tend to be closest to ideal behavior. And it says also high temperature. If you have one gas at a higher temperature than the other, then the particles in that gas are traveling faster. And that's what we have to get at now. So in a perfect world then, we'd want very few particles and we'd want them traveling very fast. If they were traveling very fast, they'd have no influence on each other. They wouldn't be near each other for long enough. And that's the idea you want. Now, I'd expect you to know that. Under what conditions does a real gas come close to ideal behavior? And we look at that in an exam question now shortly, just to see how you'd handle that. They'll name a real gas, you see. They'll say something like nitrogen or oxygen or carbon dioxide and ask you, why is that not close to ideal behavior? And you'll have to give reasons for that, okay? So now, please, I expect you to know that low pressure means little or no collisions, okay? And high temperature means traveling very fast. And that will be very important in trying to follow that up. And before I leave that go now and finish this little part, can I remind you again, please, that the volume of a gas is simply the volume of its container. Okay? That the temperature of a gas is the speed at which the particles are moving. And the pressure of a gas is the number of collisions. That's all very important in trying to put that together, and I hope that you would take that as important factual material. Very good? Now look at this for a moment again, please, and let's see where we're going. Masses, gases and moles. We've done masses in a previous unit. I've done the early part of gases with you, and I'm now about to repeat this section of it here, okay? I have dealt with the kinetic theory of gases. You'll be asked for the assumptions of this theory, and you'll be asked what are the flaws or the limitations of those assumptions, okay? So just prepare that in advance, please, and you'll be fine. I'm about to start now on ideal gas with you, and look, we've dealt with that already. Real gases at low pressure and high temperature. What is it about real gases at low pressure and high temperature? The answer is they come very close to an ideal gas, which is what I'm going to deal with now. Okay then, you'll be asked to define, literally define an ideal gas. And I think you have to work with that in mind. What is an ideal gas? And there's a simple definition for it, okay? And there's not much room for maneuver with this now. You'll have to take it at face value. This is a gas which obeys all the assumptions of the kinetic theory under all conditions. Now, there are some gases, and they obey most of the assumptions of the kinetic theory most of the time. But that won't do you now. That won't do you. You'll have to do better than that, okay? You'll have to accept that you'll be working with this in terms of whatever is involved here. It must be for all temperatures and all pressures. Again, I'm repeating, an ideal gas is a gas which obeys all the assumptions of the kinetic theory under all conditions of temperature and pressure, which is a kind of way of saying always. It always obeys all the assumptions of kinetic theory. Now, at the risk of sounding silly, an ideal gas doesn't exist. It's a concept. Okay, and saying it doesn't exist, it doesn't read well. But I mean, you need to understand that. It's something we aspire to. We all aspire to being the ideal man or the ideal woman. Okay, and the ideal gas is a model that we aspire to, and that's what it would be. Now, they'd ask you that very deliberately. What is an ideal gas? This is a gas which obeys all the assumptions of kinetic theory under all conditions of temperature and pressure. Now, I've appealed to in previous units, stop learning these as definitions, as words. Think of the concept, think of the idea you're communicating, and you'll do very well. Okay, that's important now that you've worked your way through that. Okay then, now we've a very important equation coming up, which is one I've alluded to already, and I said, you know, if you have calculations to do, I would prefer you'd be using this one. It's much easier in all sorts of ways, but we have to be careful. It's called the ideal gas equation, written in the study plan as the equation of state for an ideal gas. Now, be careful with it because you need to work your way through this, however we're going to do that, okay? And I'm going to deal with that now. As follows. First of all, now, last unit we said PV over T is a constant for all gases. Okay? We were saying that there's no point having a volume of a gas if you don't know the pressure and the temperature at which it exists. And that's what this is about here. PV over T is a constant for all gases, right? If you happen to be dealing with an ideal gas, then the constant is a very specific value. I'll write it up here in the corner of the board. It's 8.31, and I'm just going to write metric next to it. Now, that's available in the formula tables. I wouldn't worry about that at all. That's available to you, and you'll get it in the log tables. Page 47, I think, is where you'll find it, okay? But it's available to you in the exam. It'll be printed on the front of the paper as well. That is a constant for 1 mole of ideal gas at STP. Do you know what STP is? Standard temperature? 273, to be precise. You'll get it in your formula tables again, 273.15. And the standard pressure is 1.015, 10 to the power of minus 5 pascals. Do you remember this? Okay, and we said 101 kilopascals. Okay, you remember that, okay? They're standard temperature and pressure, but you can look them up. You can look them up, so please just know where to find them. You must be aware that this is metric units, SI units or metric units. Be very careful. So, there is the formula, and sorry, you don't need to derive this now, you just need the end result. PV over T equals R, which is a constant. Okay, is a constant, okay, for 1 mole of ideal gas. For 1 mole of ideal gas, okay? If there's any gas, to be K. For ideal gas, it's R, right? And therefore, for N moles, it would be PV over T equals N times R, which brings us to the famous formula that we need. Now, this is an invaluable formula. I'm asking you to take particular care with it. The ideal gas equation, PV equals NR times T. Now, folks, that's very, very important, and you'll do lots of calculations with this. I'd strongly recommend this to you. Before I say anything else to you now, that is the constant, which is metric. So everything else in that formula must be metric, and that's the most likely error you're going to make. I have it there as a warning for you. Will you accept that, please? Okay, note, all quantities must be in metric units. All quantities must be in metric units. If they're not in metric units, we have an issue, right? You'll just get the wrong result. And I'm going to go through that with you now briefly. That has to be in pascals. They often give you pressure in kilopascals. Don't forget to multiply by 1,000. This volume is the one you're likely to get wrong. That could be given to you in any units. Litres or centimetres cubed are very common. You can't, they're not metric. The metric unit is meters cubed. Now please, you need to get a sense of proportion here as to what a metre cubed would be. It's a huge volume. But you have to express all your volumes in meters cubed if you're using that formula. Okay, very, very important. I'll move on for the moment. I'll come back to that moment. That's the number of moles. I'll be dealing with that in the next unit. But that's the number, it's the number of particles, number of moles. We'll be dealing with that next. That's a constant, and it's metric already. And this is the other one I have to get you to watch. The temperature must be metric as well. The metric unit of temperature is Kelvin. Be careful, Kelvin. And we need to convert the 3 of them now. In every time you use that formula, please, that's a health warning now. You're going to screw up here very quickly if you don't be aware of that. Please understand, that guy is metric, so everything must be metric when you're working with this formula. And always list your data, okay? So I'm reminding you, if you got something like 101 kilopascals, you'd write that as 101 by 10 to the power of 3 pascals. Okay, and that's exactly how you'd write it now in the exam. And if you got here, supposing you got, we will say 75 centimeters cubed. 75 centimeters cubed. Can you read that, okay? 75 centimeters cubed. If you were given that, you'd have to convert it to meters cubed. And that would be 75 by 10 to the power of minus 6 meters cubed. Now, that's the figure I want you to watch. Okay? 10 to the power of minus 6. There are 1,000,000 centimeters cubed in a meter cubed. Now, please understand, I keep shaking my hands at you, but a meter cubed is a huge volume. Okay? You'd never have that in a test tube. If you were walking around with a test tube of a substance, right? A test tube full of gas. Do you realize that's a tiny amount you'd have, 10 to the power of minus 6. Very important that that conversion is there. Maybe I need to mention something else to you. Supposing they gave you liters. Suppose they gave you liters. No, sorry, that was pressure. This is volume. Suppose they gave you liters. Suppose you had 1.5 liters of a gas. That'd be big enough now, wouldn't it? Have you some sense of how big 1.5 liters would be? Yeah, a large bottle would be, okay? 1.5 liters. That would be 1.5 by 10 to the power of minus 3 meters cubed. Meters cubed, okay? Meters cubed. Okay, very important. Now, there's 1,000 liters in a meter cubed. 1,000 liters in a meter cubed. Be careful now, those two conversion factors. Now, that's not correct scientific notation, but it's the correct value. I'm okay with that. When you put that into a calculator, it'll take care of itself. It'll be fine. Now, please, that's exactly what you should do in the exam. And lastly, then, if you had temperature. If they gave you a temperature, I'm going to say 100 degrees just to keep things together, okay? 100 degrees Celsius. Then you have to convert to Kelvin. You'll be adding 273 to that. So you'll get 373 Kelvin. Very important you do that. Now, the exercise I've engaged in on the board there is very important for all calculations. It's very good practice when you're solving what are traditionally known as problems, wherever that name came from. When you're solving a problem, it's a very good idea to list the data they actually gave you on the exam question. Literally take them down. And then the ones that need changing, you change them. That's very good practice, because you'll always be aware then of being, that units must be right. And only now are you ready to pop those figures into that formula, and you're likely to be able to do your calculation from there. Now, what's the primary function of that formula, would you think? And the answer is a very simple one, really. Whenever you're talking about a volume of a gas, as I've told you in a previous unit, you will always know the pressure and the temperature. So if I give you a volume of a gas at a stated pressure and a stated temperature, you can calculate the number of moles in that container. Okay, there's your gas syringe. Okay, there's your piston and there's your clip at the top of it, and there's your gas inside in the gas syringe. And you'd get your volume here on this scale, as you know. That's the way it would be, yeah? And you'd read the volume there. So you'd get the volume of your gas there. You'd know the temperature of the room. You'd know the pressure of the room from the barometer, temperature from the thermometer, pressure from the barometer. So you'd have P, T, and V. So you could very quickly tell me how many moles are inside in that container. And that's the primary function of that. Now, I would strongly recommend that formula to you over the combined, the combining gas equation we met over P1V1 over T1 equals P2V2 over T2. I said to you at the time, there was a better formula coming up, and I would prefer you were using that one. So for the last time, then I'm saying to you, whenever they give you the volume of a gas, and they state the pressure and temperature at which it exists, you can calculate the number of moles in that container. And that's it. That's exactly what you'd want from that, okay? And that's very good. That's what we'll be trying to deal with there with that. And I think that would be a useful place at which to stop just for the moment, all right?